Thanks for joining us this afternoon. My name's Ed Gash. I'm a business development here at Mobilise. I'm joined by one of my colleagues, Gareth Davies, who is one of our cloud consultants and Kubernetes certified administrators.
Hello, everyone.
Today, we're just starting off, what we're hoping is going to become a new series of webinars looking at key components of modern cloud infrastructure and technologies. So today we're going to take a look at containers, Docker and Kubernetes, and what kind of impact these are having on the industry, whilst also why people should are adopting these tools, and also take a bit of a peek at them as well. So today, we're going to talk a bit in general about some of the changes that have happened in recent times around development practices that have sort of led to the rise of the use of containers. We're then also going to look at the differences between containers and virtual machines. We're then going to look at some of the use cases that we see from our customers of how they're utilizing containers, some of the problems people experience, and then we're also going to look at Kubernetes and how this is really changing how people use containers and also the cloud internally as well. And we're going to finish that off with a demonstration, and if we have some time left over, we'll go through look at any questions that have been answered, that have been asked, and provide answers to those. So first of all, I just want to give you a bit of background about Mobilise. So Mobilise is a leading provider of public cloud enablement services. So this means that we help customers in their journeys towards the cloud, whether that be in designing, implementing, migrating, sort of optimizing processes, but also providing managed services to help ensure that our customers get the most from their spend with public cloud providers. Mobilise is also a certified, Kubernetes certified service provider. We're one of only a handful in the UK, and as a company, we are our team is UK based and provide all of our services out of here. As an organisation, we are ISO 27001 and 9001 accredited to give our customers the assurances that our processes are robust and in line with industry expectations.
So let's have a look at a brief history and how the industry arrived at Kubernetes solution. In the past, applications were built as large monolithic systems deployed to servers and data centers. This made the applications hard to support and maintain, as well as difficult to reuse and develop, as the internal components of the application are so tightly coupled. This meant that testing took an extremely long time, as a change to one component meant regression testing the whole application, leading to a slow build and release cycle. If a customer wished to have a new change implemented quickly to adjust to a new trend in the market, this often proved difficult and expensive. The move to virtual machines meant that businesses could downsize their infrastructure and reduce costs in data centers. It didn't, however, solve the application problem. Since then, a new way of designing and building applications called microservices has ushered in a large change in the way applications are architectured and deployed. The idea being that instead of having one large application, the individual components are split out, decoupled, and deployed independently of each other. This speeds up development, allowing individual components to be tested far easier and supported with a greater understanding. No longer do application support staff have to understand how a whole application works, but just the parts they're responsible for. Developers can easily reuse components in their new applications, and testing can be carried out against specific parts of the new application. Containers are a natural fit for microservices, as they are lightweight, just like the microservices they run, and enable businesses to easily take advantage of cloud practices, such as auto-scaling, which is replicating our applications to meet customer demands, just-in-time execution, shutting down the application when it's not being used, and maximizing resources through scheduling. The idea of containerization has been around for a long time. However, it wasn't until 2013 when Docker emerged that containers exploded in popularity. To date, over 3.5 million applications have been placed in containers using Docker technology, and over 37 billion containerized applications have been downloaded. The application container market is expected to grow rapidly from annual revenue of $750 million to $3.4 billion by 2021.
So, with that move in development patterns, the rise of microservices and containers, funny enough, you can't read a blog or go to a conference without somebody there talking about containers or Docker. So, what we're going to do is take a bit of a look on how, of what these containers are and how they compare to traditional methods of deployment. So, what are containers? Containers are a method of operating system virtualization that allow you to run an application and all of its dependencies in a resource isolated package. But, you're probably there saying, well, we've been able to do that in virtual machines for years. And, why is this new? What's so different about it? Well, so Gareth's going to cover off how the stack of the virtual machine is a bit different to the containers and what this means.
So as you can see from this slide, virtual machines work by packaging the operating system and application together. When you have several virtual machines on the same server, this creates a lot of overhead and limits the amount of applications you can deploy. Containers, however, work differently because they only contain the application, libraries, and binaries that they depend on. The only operating system on the server is the host operating system, which is utilized by Docker to run the containers directly on the host machine. This means we can fit more applications onto a server running containers than we can virtual machines. As an example shown in the diagram, if we want to run 2 copies of application A and 1 of B, then we need 3 virtual machines complete with their operating systems, bringing the total to 4 operating systems, including the host OS. In the container example, we could run 4 copies of application A and 2 copies of B on just 1 operating system and still consume fewer resources than the virtual machine example.
But, virtual machines still have their place. There are still some benefits to using virtual machines, such as all of the operating system resources are available to applications, which is a great fit if you do have apps that require all of the OS resources and functionality. But also there is a very mature ecosystem of tools for management, for security, but also a wide understanding across the industry about how to implement virtual machines and how to manage them. But that being said, containers do provide a number of benefits, that are quite compelling. So things such as reduced IT management. So with fewer servers deployed, you don't need as many sysadmins managing the server estate. Reducing the size of your snapshots means that there's less cost incurred through the storage and transfer of those. There's a much faster startup time on applications as well. So because the containers are much more lightweight and not having to boot the OS every time, containers are generally starting in milliseconds versus virtual machines that can take tens of seconds to load. And finally, reducing and simplifying your security updates. Going back to Gareth's earlier picture showing the number of different operating systems you have to support, you also then have to apply security patches and updates over time. Whereas with containers, you only have one security update to apply on the host, on the host OS. But it's great to see all of these benefits on paper. But what does that actually mean in the real world? So let's have a look at how we see people using them.
So we've got a list here of some use cases. So from the top, we've got distributed applications and microservices. So something we've already touched on, breaking down large applications into smaller decoupled microservices to facilitate easier repeatability, support, maintenance, and coding practices. Batch ETL jobs, so you can package your jobs into containers to maximize available resources You can even spin up the same instances of the job and run them in parallel since they're in an isolated container. Once finished, they can terminate themselves and free up resources for other containers to run. Continuous integration and delivery. Build a CI/CD pipeline based on containers, which package applications and deploy through containers. So you always have the deployment tool set at a known version and configuration. Cost saving, as we mentioned, reducing infrastructure footprint, less servers, less spend. Portability, lift and shift your containers from one cloud provider to another or to on-premises, or even bring the two together into a hybrid cloud solution. Scalability, easily scale out copies of your containers to provide high availability. Greater development, know more it works on my machine, but not in a production environment. Have your images of your application that work exactly the same in all environments from dev through to production due to the nature of containers. Collaborative development. If a developer is having trouble, just download their container to your machine and work on it collaboratively. And finally, server consolidation. Consolidate your estate of virtual machines to a fixed set of Dockerized servers so there is less to support and less to manage.
So this all sounds great, doesn't it? But it's not all smooth sailing. So we're also going to look at what are some of the problems that we face when running containers.
So we run into similar kind of problems with running multiple containers as in running multiple virtual machines, mainly managing them. It's difficult to keep track of many running containers on a server without a visualization tool or abstraction layer to manage them. So imagine having a Dockerized server with 50 plus containers deployed to it. How do we automatically scale these containers in size to meet demand? How do we monitor the health of our containers? How do we make sure we remove unused containers or orphaned containers? How do we route traffic from outside our system through our infrastructure into the correct container? So a lot of the problems we faced when trying to run containers manually have now been solved through container orchestration, the most popular product of which is Kubernetes. So what is Kubernetes? Kubernetes provides a platform for the orchestration of containers, enabling us to maximize server resources by scheduling the running of pods. Now, pods are a Kubernetes term for a group of containers that are deployed together. Usually the same application is duplicated within a pod. Now, a Kubernetes platform is made up of a master node, which handles all of the administration, and several worker nodes, which run the pods. We can increase the number of worker nodes based on how many pods we have running. Scheduling means that we can squeeze as many pods as possible onto each worker node, allowing us to maximize the resources used and possibly shut down unused worker nodes. Through the use of Kubernetes dashboard, your container estate can now be visualized, allowing administrators to better manage and support their systems. Kubernetes will manage all of the networking and resourcing of your estate, so your microservices can easily talk to each other through services, a feature of Kubernetes which acts as a virtual load balancer. Allowing Kubernetes to manage all of the networking, resourcing, and deployment means we can focus on what really matters, creating and developing new services for our customers. So what about the history of Kubernetes? The origin of Kubernetes can be traced back to the early 2000s and Google's internal Borg project. Google's Borg system is a cluster manager that runs hundreds of thousands of jobs for many thousands of different applications across a number of clusters, each with up to tens of thousands of machines. As Google's own requirements shifted, the technology was updated to reflect this change. In 2014, Google then created a new open source project called Kubernetes. Kubernetes is now supported by over 830 contributors that have collectively put in 237 person years of coding effort to date. It recently graduated as the first project from the Cloud Native Computing Foundation, which signifies its maturity and resiliency at managing containers at scale.
So it's great to see that Kubernetes is being so widely supported, but as with all of these, Kubernetes and with Docker, they are very, very new technologies still in comparison to traditional virtualization tools. So maybe if we take a look at some of the other organizations that are already trusting Kubernetes with their workloads, you can see this from the Kubernetes website. You've got people like Goldman Sachs, IBM, ING, Capital One, all of these very large organizations are already moving their workloads using containers and Kubernetes to deliver additional efficiencies within their estates.
So why use Kubernetes? Kubernetes eliminates infrastructure vendor lock-in by providing core capabilities for containers without imposing restrictions. It achieves this through a combination of features within the Kubernetes platform, including pods and services. Kubernetes can be deployed to all major public cloud providers, as well as being installed on premises. Some of the major cloud providers even provide a managed Kubernetes service. A modular approach enables faster development by smaller, more focused teams that are each responsible for specific containers. Concepts like namespaces allow us to segregate applications within the cluster to provide container isolation and security between applications. Deployment features like horizontal autoscaling, which is duplicating our app based on containers resource usage, or rolling updates, which provide near zero downtime, or canary deployments, which enable you to test your new deployment in production while slowly scaling it up and checking results while slowly scaling down your previous deployment. Kubernetes marks a breakthrough for DevOps because it allows teams to keep pace with the requirements of modern software development. In the absence of Kubernetes, teams have often been forced to script their own software deployment, scaling, and update workflows. Some organizations employ large teams to handle those tasks alone. Kubernetes allows us to derive maximum utility from containers and build cloud-native applications that can be run anywhere, independent of cloud-specific requirements. Now businesses can easily and quickly get their applications into a production environment with the flexibility needed to deploy beta or prototype pieces of work.
So it's all really good that we can talk about Kubernetes and talk about containers, but it's probably much better if we provide a short demonstration about give you a guide around the Kubernetes platform and some of its capabilities. I will say we're not going, on our first demo we weren't going to risk a live demo, so Gareth has recorded a walkthrough which he'll talk through now.
So this is a Kubernetes cluster we've deployed to Amazon's public cloud offering. You can see here we've got the Kubernetes dashboard, which gives us all kinds of information like CPU usage and memory. We can see here we've got 3 nodes, worker nodes in our cluster. And if we go into overview, you can see there's not much here. We've got some default services and secrets and node deployments. So what we're going to do is deploy a simple Nginx application. So we'll do this by using YAML files that you can see here. So we have a deployment YAML file where we've got type deployment, app Nginx. We're going to be using Nginx version 1.7.9, and we're going to be exposing it on port 80. So if we deploy that using kube control, which is a client-side utility for talking to Kubernetes, you can see there it deployed rather quickly. So if we refresh the page, we can see we have our Nginx deployment. So you've got a bit more information. If you click in here, you can see things like creation time, the version of the image that we've got. So the Nginx image was pulled down from Docker Hub, which is kind of like an app store for Docker images. And we did it using a rolling update. So next, we need to look at exposing that deployment. So we need to create a service so that we can access that deployment. So you can see here, it's a relatively small YAML file. It's looking for the app Nginx on port 80, and we're going to create a type load balancer service. So what this load balancer service will do is create an AWS load balancer so that we can access our application from the internet. So if we just apply this YAML file, once again, very quick, back to our dashboard, and we can see we have a new service called Nginx, port 80. And if we click on there, we can see we have this external endpoint, which is our Amazon load balancer address. So Kubernetes has gone off and created this resource itself, speaking to the AWS console. So if we look in here, we can see our load balancer resource, our address, and you can see there are no healthy instances yet. We have to complete the health check first. So while we're waiting on that, we will have a look at how we can access resources through the kube control client. So we can get the deployment information there, and we can also describe that deployment. And you will see a lot of information here. So some of it you will have seen in the deployment YAML, but Kubernetes will have added certain things like events towards the bottom. You can see the history of the deployment. So if we now look at the pods, which were created by the deployment, so the pods actually house the containers that we need to get to. So if we describe this pod, you can see some information about the container. So you can see the ID and where it got the image from Docker. You can see the history information or event information about the container, about the pod. So you can see it was created and pulled, and it's all done rather quickly as well. If we now look at the service, you can see we have our Nginx service of type load balancer. So if we have a look at that, you can see a little bit of information. So it's looking for the app Nginx, load balancer type, and the port that we're pointing to. So now if we go back to the AWS console, those servers should be healthy. So now we can try and hit our pod through the external load balancer. So if we try and hit it on port 80, yeah, we get the welcome to Nginx standard HTML page. But just to show you that we actually did this deployment properly, we'll go in and edit that page using kubecontrol's exec utility. So you could compare this to SSHing to a server perhaps. So this allows us to go into the pod file system, and we can install some editor utilities. So when we pull the Nginx image, the Nginx image only comes with Nginx on it. It's like a bare bones image. It doesn't come with any unnecessary things like editors. So that's why we're having to install an editor so that we can edit our HTML page. So we've installed Vim, and now we're going to edit the index page. I can type it correctly. So you can see here the page we just saw in the browser. So let's just change that to welcome to a Mobilise webinar. And we'll change some of the body as well. Welcome to Mobilise webinar. And we'll get rid of most of this text and just change this last bit here. So thank you for attending, and we'll save that file. So when we go back to our browser, refresh the page, there we go. Welcome to Mobilise webinar, thank you for attending. You can see the address there, the external load balancer address. So if we come out of our pod and we come back into the kubectl command, just to show you there is still one pod running. But what we can do is edit our deployment now. So edit our Nginx deployment, where you get all of this YAML. And the bit we're interested in is the replicas, which is how many of that container we want running in the pod. So I'll change it to 8. And you can see within seconds, we have 8 Nginx images running. So you can look through the dashboard as well. Overview, and you can see it's all green. Got our deployments, pods, and all of our Nginx containers here. And that just shows how quickly and easily you can scale up resources within Kubernetes.
Perfect, thanks for that, Gareth. So, yeah, we've gone through, I know we've gone through quite a lot of information in quite a short space of time. So I think what we are going to do now is if we take a look and see if there are any questions that have been asked, and yeah, let's dive into a bit of Q&A if possible. So, okay, just looking here, we've got one of the questions that we've got here is, how does Kubernetes handle a node failure?
Right, so Kubernetes is designed to be resilient out of the box. So whether it's a master or worker node failure, when a master fails, the nodes of the cluster will keep operating, but there can be no changes to any of the pods or services until the master is available again. So what tends to happen is the master node's database can be backed up routinely and then restored in the process of bringing a new master back online. When a worker fails, the master stops receiving messages from the worker. If the master does not receive updates from the worker node, it will be marked as not ready. And if a node is not ready for 5 minutes, the master reschedules all the pods running on that dead node to other available nodes.
Okay. So just looking at another one here, one of the other questions we've got here is, what kind of security practices does Kubernetes use?
So there's quite a lot of built-in security Kubernetes. One of the main ones you could start with is to ensure that your images that you deploy into Kubernetes are free of vulnerabilities. So you can do that by implementing continuous security vulnerability scanning, regularly applying security updates to your containers by updating them and redeploying them. You can ensure that only authorized images are used on your cluster. So you can do that by using a private registry to store all of your images, and then use your continuous integration pipeline to enforce that only images from that registry are used on your cluster. You can also limit direct access to Kubernetes nodes. You can use policies to attach to users so that certain users can only access specific resources in certain namespaces. You can also define resource quotas so that you can limit the amount of CPU or memory a pod can use to prevent DOS or noisy neighbor scenarios. You can apply security context to your pods so that, for example, you can specify a pod can't run with root privileges. And finally, you should probably ensure that everything is audited and logged. Yeah, that's it.
Okay. I'm just conscious of time, but so we're just coming up to the end of the half an hour. What we'll do, if it's okay with everyone, is we will. Any questions that we haven't been able to answer, I can see that there are a few more. We will go through independently and answer them after the webinar. I just really want to say thank you to everyone that's joined us today. I hope mine and Gareth's first attempt on this webinar series has been useful, whilst also being enjoyable at the same time. if you do have any other questions, you please do get in touch. You can contact us by email. And also, if you're interested in further webinars that we may be running, please follow us on Twitter. Or, if you are currently embarking on some kind of cloud migration or Kubernetes project or whatever it might be, and you want to, talk to someone that could help, please get in touch. But other than that, thanks a lot for joining us today, and hopefully we'll hear from you'll see us again soon.